Now we are going to start with the Rankine cycle. Okay, Rankine cycle is the actual cycle on which the steam power plant works. So in the last lecture we have seen the ideal cycle for what the steam turbine is ideally, okay, ideally is going to work. Okay, that means in the previous lecture we have read about the steam power plant running on a Carnot cycle, which is purely imaginary. Okay, because that is an ideal cycle. Okay, so whatever thing was going on in the last lecture was purely imaginary. Now Rankine cycle is the real cycle, which is going to, although it is having reversible processes all over it, okay, to complete the cycle, although this is considered as the real cycle which is going to be used for steam power plant. Okay, so let us start with the Rankine cycle. Okay, now if you see, the mechanism or the layout is going to be same. Okay, it is going to be pretty much same. Okay, the only thing we are doing is we are changing the cycle. Okay, we are changing the cycle. Previously we had added heat, okay, added heat and rejected heat. We have passing through the condenser, we have made slightly liquid and slightly vapor. Now we are changing it to complete liquid. So such small changes are there so that we can change the cycle. Okay, we can change the cycle. In place of Carnot cycle, there will be now Rankine cycle. Okay, otherwise everything is going to be same. Only the points in the TS diagram is going to be different now. Okay, only the points in the TS diagram is going to be different now. That means what is the main difference? As it is going through the same mechanism, still this diagram is going to be same, just because the heat addition or the conditions at which we used to add the heat, conditions at which we used to reject the heat are going to be different. Okay, so that is the main difference. Now for the first process is going to be 1 to 2. Okay, the first process is nothing but it is a pump. Okay, or you can say reversible adiabatic compression. Okay, pump is nothing, pump also does compress. Okay, so 1 to 2 is nothing but the pump is pulling in the water coming out of the condenser. Okay, so 1 to 2 is nothing but reversible adiabatic compression. Okay, so due to the compression the temperature increases. Okay, reversible adiabatic compression, the temperature increases. Okay, now second thing is what? Second thing is boiler. Boiler is what? Boiler is nothing but our heat addition machine. Okay, or the machine part which helps us to add the heat. Okay, so we use now we are going to reversible constant pressure heat addition. Okay, now we are going to add the heat at constant pressure. Okay, add the heat at constant pressure 2 to 3. Okay, now in the Carnot cycle you have seen that this point goes from there to there. Okay, that means after increasing the pressure in Carnot cycle, the end product from the condenser come at this point. Okay, come at this point, but the end product from the Rankine cycle, okay, that means the end product from the condenser of Rankine cycle comes at this point. That means what? From the condenser of the Carnot cycle, the product which is coming out was a mixture of liquid and vapor. Okay, now in Rankine cycle, whatever the product is coming out of the condenser is nothing but saturated liquid. Okay, it was saturated liquid. Now in the Carnot cycle, while you used to compress it, okay, while you used to pass it through a compressor or a pump, it used to rise the pressure of the substance that was coming out of the condenser. Okay, it used to rise the pressure. Due to rise of that pressure, it used to reach at a point where it used to be a saturated liquid. Previously, before the compression, it had a mixture of liquid and vapor. Now after increasing the pressure in Carnot cycle, it reached to a point where it is saturated liquid. Okay, now in Rankine cycle what happens? The product already is saturated liquid. Now you are increasing the pressure and it is going to be a subcooled liquid. Okay, that means it is going to have a at that pressure it is going to have a point where it is a liquid which needs more and more entropy. Okay, now it has to cover this much of entropy to become saturated liquid. Saturated liquid means what? It is nothing but a state where it is on the verge of evaporation. Now just it will evaporate. Okay, now in Rankine cycle, after the compression, it reaches to a point where it requires more entropy. Okay, it requires more entropy so that it becomes saturated liquid. Okay, the product was already saturated liquid. Okay, now in this Rankine cycle, the boiler consisting of three other parts. Okay, the boiler consists of three other parts. One is economizer, one is evaporator, and one is superheater. Okay, now what is economizer? Economizer is a device which used to heat up the liquid. Okay, it is used to rise the temperature of a liquid. Okay, before the boiling starts. Okay, before the evaporating starts, it is used to rise the temperature. Suppose there is water at 50 degrees centigrade. Now economizer will help you to reach the it will help you to make the temperature of this 50 degrees centigrade liquid to reach a temperature of 100 degrees centigrade. After reaching to 100 degrees centigrade, it is going to start evaporating. Okay, it is going to start evaporating. So the device which makes you reach its temperature from that temperature to the boiling point temperature is nothing but economizer. Okay, so economizer is, what is economizer? Through economizer you are going to add heat from 2 to 2 dash. At constant pressure you are going to heat up to 2 to 2 dash. Now what it is having? At point 2 it is in such a state that it requires more entropy to become saturated liquid. Okay, now through economizer you are going to add the heat such that at constant pressure it reaches to point 2 dash. At constant pressure it reaches to point 2 dash. Okay, 2 dash, at point 2 dash it has reached means what? At high pressure condition. Okay, this is high pressure, pH. At high pressure condition, okay, at this point what is going to be the temperature is going to be the boiling point temperature at that pressure. We all know that at different pressure the boiling point temperature is always different. Okay, if the pressure is going to be low, then the boiling point temperature is also low. Okay, if the pressure is very much higher, then the boiling point temperature is also higher. Okay, so that means at this pressure, after coming out of the condenser, it is going to have a pressure at this point. So at that time, at that pressure, okay, that means at this pressure, P low, at this pressure, this temperature is going to be your boiling point temperature of the water. But since now you are increasing its pressure, you are increasing its pressure from point 1 to 2, you are increasing its pressure. Okay, now what will happen? At this pressure, okay, at this pressure, this temperature is going to give you the boiling point temperature of the high pressure liquid. Okay, high pressure liquid. So economizer does what? Economizer takes it to the point from where it can start evaporation. Okay, so 2 to 2 dash is nothing but the heat addition process by an evaporator, and 2 to 2 dash what happens? It goes from completely liquid, subcooled liquid region. Subcooled region means what? It is far away from the saturated liquid portion. Okay, in the left side it is far away from the saturated liquid line. That region is called subcooled region. Okay, so the water has, after compression, the water has reached a subcooled region. Economizer is going to help us so that we can give heat. Okay, we can give heat in such a way so that it reaches to a temperature. At constant pressure, it reaches to a temperature where it can be now start evaporating. Okay, where it can now start evaporating. That is, by at constant pressure, we are reaching to a saturated liquid state. Okay, saturated liquid state. The second thing is what? The second thing is evaporator. Inside the boiler itself, okay, inside the boiler itself there are three parts. One is economizer. Second thing is evaporator. Evaporator is what? Evaporator is nothing but it is now the complete phase change process is going to be there. Evaporator helps us to change the phase from liquid to gaseous. Okay, so as we all know, inside the vapor dome, the constant pressure line is again a straight line. Constant pressure line is because evaporation process or phase change process, the temperature remains constant. until and unless the whole liquid is going to evaporate, the temperature is not going to change. So this is the reason at TS diagram the constant pressure inside the vapor dome is always going to be our constant pressure process, and it is going to have a straight line. So evaporator does what? Evaporator takes the liquid from point 2 dash to 2 double dash. Okay, it takes the liquid from the point 2 dash to, that means it takes it from saturated liquid where it is in the verge of evaporation to 2 double dash. 2 double dash means what? 2 double dash is in the line of saturated vapor. Saturated vapor means what? Where it has just completed the evaporation process. Okay, that means with the help of evaporator we are going, okay, we are converting the saturated liquid to saturated vapor. Okay, so this is the work of evaporator. Now there is superheater. Another one is superheater. Superheater means what? After the steam is formed, if you again rise the temperature of the steam, that process is known as superheating. Okay, so at point 2 double dash, we all know, since it is in the saturated vapor line, at 2 double dash the complete liquid has been converted into steam now. Okay, still we are rising its temperature from 2 double dash to 3. From 2 double dash to 3. That is also a constant pressure heat addition process. Okay, so with this heat addition, the temperature of the steam rises from T2 dash to T3. Okay, so we are superheating so that the temperature of the steam again rises. Okay, so what is the heat addition process now? If you look at the heat addition process is going to be in 3 steps. One in economizer from 2 to 2 dash, one in evaporator from 2 dash to 2 double dash, okay, and third one is superheater from 2 dash to 3. Why do we increase the temperature? Okay, why do we increase the temperature of the steam again? The higher the temperature would be, okay, the exit, okay, or the steam quality at the exit of the turbine would be good. Okay, the more it is high temperature, if you go for higher temperature again, the exit will come here. Okay, or exit products of the turbine will come here. Okay, so the more you heat the steam, the exit products of the turbine will reach a point towards the saturated gaseous line. At the point, as much as it is towards the gaseous line, the steam quality is going to be higher. Okay, or good. Steam quality is going to be good. And steam quality, if the steam quality is good, what happens? The erosion does not take place in the steam turbine. Okay, that means at any point in the turbine, whatever the substance is in the turbine does not go to a wet region. Okay, that means whatever it is coming out is never going to be the liquid plus vapor. Even if it is going to be negligible. Okay, because at this point, at Rankine cycle, whatever the product is coming out, what happens? At this point, whatever the product is coming out, at Rankine cycle, it is going to have a higher value, higher steam, higher quality of steam. Okay, the exit product of the turbine will be higher quality of steam. Now, if you compare with the Rankine cycle, you will see that the Rankine cycle was nothing but 1 dash, 2 dash, 2 double dash, and 4 dash. Okay, you can say. So this was our Carnot cycle. Okay, ideal cycle, and this is our 1, 2, 3, and 4 is our Rankine cycle. 1 dash, 2 dash, 2 double dash, 4 dash is our Carnot cycle. Okay, by Carnot cycle we used to get this. Now you can say that the work done by the Rankine cycle at the same pressure. Okay, if the temperature is not mentioned at Carnot cycle, if you take the Carnot cycle, then this is the temperature, highest temperature for Carnot cycle, T2 dash. Okay, we are saying that for Carnot cycle and the Rankine cycle, we are not fixing the temperature. Okay, fixing the temperature. Now, if you are, because in the Rankine cycle you are superheating the vapor, in Carnot cycle you did not do it. So, in such cases, the work done by the Rankine cycle is more. Okay, work done by the Rankine cycle is more than the Carnot cycle. Okay, but don't confuse it as that I have told that Carnot cycle gives the highest Carnot cycle gives the highest efficiency all the time. Okay, because I have mentioned that only when the highest temperature and lowest temperature, maximum temperature and minimum temperature is fixed for any two cycle and one of them is Carnot cycle, then Carnot cycle is going to have the higher efficiency. But we are saying here clearly that at Carnot cycle whatever the temperature is there is not as same as the maximum temperature. Maximum temperature of the Rankine cycle is higher here. Okay, through the Rankine cycle we are increasing the temperature of the steam. That's it. Okay, we are not going to analyze the Carnot cycle with respect to the maximum temperatures. Okay, but we can say that whatever experiment what we have found out of Carnot cycle, now we are intentionally increasing the temperature to get the work done by the turbine, more. Okay, so for turbine it is going to be, for work done by turbine for Rankine cycle it is going to be nothing but enthalpy at state 3 minus enthalpy at state 4. Okay, whereas by work done by turbine in Carnot cycle was enthalpy at 2 double dash minus enthalpy at 4 dash. Okay, this is our work transfer difference. Okay, so from this diagram you can easily find out what was the Carnot cycle which we have used earlier and what is now the scenario of the Rankine cycle in the same TS diagram. Okay, considering the processes of Rankine cycle. One thing we must remember that in Carnot cycle the processes of heat addition and heat rejection. In Carnot cycle, heat addition and heat rejection were at constant temperature process. Okay, at constant temperature. Whereas in Rankine cycle, heat addition is at constant pressure and rejection is also at constant pressure. Okay, but this part is always parallel to the entropy axis. Why? Because we have said that inside the vapor dome the constant pressure thing also is going to be parallel to the entropy axis, because the temperature is always constant inside the vapor dome because the phase change process is taking place. Okay, so this is the difference between Carnot and Rankine. Now we are going to compare the Carnot cycle and Rankine cycle for same temperature difference. Okay, previously in the diagram we have clearly said that for the same temperature difference we did not compare. Okay, now we are going to compare for same temperature difference. Now for having the same temperature difference we cannot superheat the vapor. Okay, now to keep the temperature same, because if you superheat the, because in Carnot cycle what happens, it just reaches to the gaseous line, it does not go further. Okay, it does not go further because all the thing is going to take place in Carnot cycle. The heat addition processing is constant pressure process. Okay, the heat addition process is at constant pressure process, constant temperature. Okay, now in Rankine cycle it is constant pressure process. So since it is in constant temperature process for Carnot cycle, we can reach up to here only. But in Rankine cycle, if we want to reach, okay, if we want to reach here, we have to finish this here only. Okay, we have to finish this here only. We cannot superheat it, because if you want to superheat, and we all know that it is at constant pressure. Okay, heat addition in Rankine cycle takes place at constant pressure. Okay, now if you want to follow the path of constant pressure, then it will automatically increase the temperature. Okay, so for same temperature, okay, for same maximum temperature, okay, this is going to be our end of Rankine cycle heat addition. Okay, end of heat addition in Rankine cycle. So from here only both the things will go into the turbine. Okay, 3 to 4 is going to be the expansion process for both Carnot cycle and Rankine cycle. Now from here you can say that 1, 2, 3 and 4 is going to be our Rankine cycle, and 1 dash, 2 dash, 3 and 4 is going to be our Carnot cycle. Okay, so this is going to be our two different cycle represented in the same vapor dome. Okay, now as you can see 3 and 4 are coinciding. The points of 3 and 4 are coinciding inside the TS diagram. That means what? That means all the values of enthalpies and specific volume, entropy, everything is going to be same in case of Rankine cycle at point 3, in case of Carnot cycle at point 3, and all the values will be same in case of 0.4 at Carnot cycle and 0.4 at Rankine cycle. All the values will be same. Because we have said that if you plot a diagram at a particular point, the values are going to be same, because these are considered as properties, and properties in a particular plot at a particular point is going to have the same value. Okay, whatever path does it follow, it does not matter, but the point, if it is coinciding to a same point, then the values at that point is never going to get changed. Okay, so that means what, enthalpy value at 3 point and enthalpy value at 4 point for both the cycles is going to be same. Okay, so that means what, H3 minus H4 is going to give you your work done by turbine for Rankine cycle also, and work done by turbine for Carnot cycle also. So we can say that work done by turbine is going to be same. If we compare Carnot cycle and Rankine cycle, work done is going to be same, but enthalpy at this point and enthalpy at this point is going to have a greater difference than enthalpy at this point and enthalpy at this point. That means what, as your temperature difference is going to be less here, that means the more here, temperature difference here is more than this part. Temperature difference at 1 dash to 2 dash is more than temperature difference at 1 to 2. Okay, so as the temperature difference is more, that means the enthalpy difference should be also more. Okay, that means enthalpy at H2 dash and enthalpy at H1 dash. Okay, that means what, difference of enthalpy at H2 dash and enthalpy at H1 dash is going to be greater than enthalpy at 2 and enthalpy at 1. Difference of enthalpy at this point is going to be less than enthalpy difference at this point. That means what, this enthalpy difference gives us what, work done by the compressor. Okay, work done by compressor was given by this enthalpy difference. Okay, so that means what, in case of Carnot cycle, the work done by compressor is more, and at this point 1 to 2 is what, work done by pump for Rankine cycle. Okay, so as it is smaller for Rankine cycle and it is higher for Carnot cycle, that means what, work done by pump or compressor for Carnot cycle is going to be greater than work done by pump for Rankine cycle. Okay, then work done by pump for Rankine cycle, it is going to be, Rankine cycle work done by pump must be smaller than the work done by compressor at Carnot cycle. Okay, now again you can see that what is going to be the heat addition process now. Heat addition process is nothing but area under the curve when you heat addition process. Okay, for the Carnot cycle, heat addition process is what, 2 dash to 3 dash. Okay, 2 dash to 3. If you project this on entropy diagram, then whatever the area it is giving, it is going to be the heat addition, total heat addition. Okay, now if you project the heat addition process for Rankine cycle, then up to 2 to 3 it is going to give us the area. Okay, so for Rankine cycle this is going to be the area, whereas if you take the Carnot cycle, only this part is going to be your area. Okay, so this part is extra for Rankine cycle. Okay, this part is extra for Rankine cycle, otherwise this covers the heat addition process for Carnot cycle. That means what, heat addition process at Rankine cycle is greater than heat addition process at Carnot cycle. Now if you find out what is going to, at which case W net is going to be same. Okay, net work done is going to be same. Now you have seen that WT is what, work done by turbine is same for both the cases. Okay, and work done by pump for Carnot cycle is going to be more. Work done by pump for Carnot cycle is going to be more. Okay, that means what, the net work done for Rankine cycle is going to be higher. Why? Because the amount of work that we give to the pump is less. What output we are getting from turbine is same, but the input work we are giving in case of Rankine cycle is less, whereas the input work we give in case of Carnot cycle is going to be higher. So net work is more for Rankine cycle and net work is higher for this Carnot cycle. Okay, so net work is lower for the Carnot cycle, but the efficiency of the Carnot cycle is always going to be higher. Because what? Because of what? Because the mean temperature of heat addition. We have seen that for Carnot cycle, okay, for Carnot cycle we have seen that mean temperature is always equal to the maximum temperature for Carnot cycle. We have always seen. But whereas in case of the Rankine cycle, what is happening? This is your one temperature and this is your one temperature. Okay, so to make the area same, you have to take the mean temperature somewhere here. Okay, we have seen the we have made you understand the concept of mean temperature in the previous lectures. Okay, so the mean temperature of heat addition for Rankine cycle is going to be less. Okay, that means for Rankine cycle, for Rankine, okay, for Rankine cycle, mean temperature of heat addition is going to be less than that of maximum temperature. That is the reason the efficiency of the Carnot cycle is going to be higher. Okay, efficiency of the Carnot cycle is going to be higher than that of Rankine cycle. And in the chapter of availability also we have said that heat, okay, heat addition at higher temperature has more significance than heat addition at lower temperature. Okay, that also we have said. So as using the same concept, we know that heat addition, that mean temperature of heat addition for Rankine cycle is going to be less than that of mean temperature of heat addition for Carnot cycle. Okay, this is the mean temperature for Carnot cycle and this is the mean temperature for Rankine cycle, which is, that means mean temperature for Carnot cycle is going to be higher than that of mean temperature at Rankine cycle. That is the reason the efficiency of Carnot cycle is always going to be same for Rankine cycle. Now in the previous board we have said that don't confuse that always the efficiency is going to be higher, than how come work done was greater in case of the Rankine cycle in the previous board. Okay, so in this board we have mentioned it clearly that for same temperature Carnot cycle efficiency is always going to be higher than any other cycle in the world. Okay, than any other cycle. Okay, so this explanation ends us to the conclusion that this for same temperature difference Carnot cycle efficiency is higher than Rankine cycle, and the total comparison of work done, work output, heat input, work net is how they are going to change is in front of you with the comparison in this diagram. Now we are going to look at some terms which is related to the steam power plant. Okay, so the first term is nothing but work ratio. What is work ratio? It is nothing but the ratio of net work output to the positive work. Okay, so in a steam power plant or in a Rankine cycle, what is going to be our positive work? Positive work is nothing but our work that has been took out from the turbine. Okay, work that has been received from the turbine due to expansion of the hot gas is known as the positive work. Okay, so in the denominator the term that will come is the work done by the turbine. Okay, and at the numerator this is going to be the W net. What is the W net? Whatever work we have been receiving from the turbine, from that some of the work has been consumed by the pump to work. Okay, that means some of the energy. So what is going to be the net energy that has been received by us? It would be work done by the turbine minus of the work which is given to the compressor or pump. Okay, so the remaining heat is known as the W net. So work ratio is what? Work ratio is nothing but the ratio of net work by the work done by turbine or positive work. Now if you compare the work ratio, for which case it is going to be higher? Okay, if you consider Carnot cycle and if you consider the Rankine cycle, for which case this work ratio is going to be higher? So as we have all seen in the last board that work done by the compressor or the pump for a Rankine cycle is lesser. Okay, for a Rankine cycle work done by compressor is lesser. That's why you have found out that W net for Rankine cycle was higher. Okay, and we have also found out that for the same temperature difference, positive work or work done by turbine for both the Carnot cycle and the Rankine cycle were same. Only different thing was net work, and net work was higher for the Rankine cycle. This thing is same for both Carnot and Rankine, but W net has been changing. W net is higher for Rankine cycle. So in that case, work ratio for Rankine cycle is going to be higher than work ratio for Carnot cycle. Okay. The next term is back work ratio. What is going to be the back work ratio? Back work ratio is nothing but the ratio of negative work to positive work. Negative work means what? Where we need to give the work. Okay, that means work that has been consumed by the pump or the compressor is nothing but the negative work, and positive work, as we have told earlier, this is nothing but work done by the turbine. So the ratio of these two is known as the back work ratio. Okay, now if you consider for which case the back work ratio is going to be higher. Okay, so as you have seen in the last board that work done by the compressor for Carnot cycle was higher. Okay, if you remember the comparison, this was the Rankine cycle and this was the Carnot cycle. So from here to here it was the work done by the compressor in Carnot cycle, and from here to here it was the work done by the compressor in Rankine cycle. So obviously for Rankine cycle work done by the compressor is less. Okay, so back work ratio for Rankine cycle is going to be less always. Okay, work done for the Rankine cycle. Okay, work done by the compressor for Rankine cycle is going to be less. So and the denominator is same for both the cases. So that is the reason back work ratio of this one, back work ratio of Carnot cycle is going to be higher than that of back work ratio of Rankine cycle. Okay, and another thing, if you add up work ratio and back work ratio, you are going to get the result one, because this is what? This is nothing but W net. W net means what? Work done by the turbine minus work done by the compressor. Sorry, work consumed by the compressor divided by work done by the turbine. Okay, and this is what? Work done by compressor by work done by. So if you add this here, what will be there? Omega. So WC and WC is going to get cancelled out. Okay, so what would be remaining after the summation? What would be remaining? The remaining thing would be nothing but work done by turbine divided by work done by turbine. So this is obviously going to be 1. Okay, so work ratio plus back work ratio has if you add up both these, then this is going to give you a result of 1. Okay, and another most important thing is, for a plant, high work ratio and low back work ratio is always required. Okay, if you want to get a maximum efficiency from or a maximum work output from a plant, you need to keep in mind that your work ratio must be higher. Work ratio is what? Net work. That means net work must be higher. Okay, and your back work ratio must be lower. That means work consumed by must be smaller and net work must be higher for a plant to get for a plant to get maximum work. Okay, to get the maximum benefit from a plant, you need to remember that we need higher work ratio and lower back work ratio. The next topic is, or the next term which you need to remember is specific steam consumption. Okay, so what is the definition of specific steam consumption? It is nothing but amount of steam required to produce unit power. Okay, that means to produce 1 kilowatt of power, okay, or 1 unit power, for production of that amount of power, what is the amount of steam you need to circulate? Okay, what is the amount of need you need to circulate through the machine parts of the steam power plant? Then that amount of steam is known as nothing but that amount of steam. Okay, that means the amount of steam is known as nothing but specific steam consumption. Okay, so that means what? It is nothing but steam. Okay, mass of steam per unit time. Mass of steam. This is m as dot. That means what? Mass flow rate. Okay, mass flow rate. So mass flow rate per unit power output. Okay, per unit power output is going to be nothing but SSC. SSC means specific steam consumption. Okay, so if you see here, power output is nothing but mass flow rate into W net. Okay, because work done per unit time is going to be your power. Work done per unit time. So in the mass flow rate there is one by time, that is mass by unit time. Okay, and there is W net. Okay, so there is W net by time is going to give you power. Okay, so from here mass of steam and mass of steam is going to get cancelled out. So the remaining thing is 1 by W net. So if you know what is going to be W net, and this is what? This is the total amount of work. Okay, now since MS is not there, only W net is there, that means what? That is nothing but work done per unit kg. Okay, because with the multiplication of mass of steam, it was nothing but total work done. Okay, since mass is not there here, no mass is not there, that means it is going to be work done per unit kg. So you can write it here kilojoule per kg. Okay, and you can also write hour by hour. Okay, we need to modify this equation, that's why we are writing hour by hour. Okay, so the hour, okay, so this hour will go up, this hour is denominator to the denominator, so it will go to numerator. Okay, so that means what, in place of SSC you can write, you can convert this hour into second. Okay, so 1 hour is equal to what, 1 hour is equal to 3600 second. Okay, 1 hour is equal to 3600 second. And what is the amount remaining, what is the amount remaining in the denominator? It is nothing but W net. Okay, W net, and the unit that this hour has gone up and converted itself into 3600 second. What is the remaining thing? Kilojoule per kg, kilojoule per kg and hour. Okay, kilojoule per kg and hour. Okay, so kilojoule per second. Okay, this is kilojoule. Kilojoule per second is again what? Kilojoule per second is again power. Kilojoule is work, and work done per second is again power. So kilojoule per second we can write it as kilowatt. Okay, so that means here you can write 3600 divided by W net. And what would be the unit? This is kilojoule per second. Okay, kilojoule per second is kilowatt. Okay, now here it is second by kilojoule, so here the kilowatt term will come in the denominator. Okay, and remaining thing is kg. Kg is in the denominator to the denominator, so it will go to the numerator, so it would be kg here, and 1 hour is remaining here. So that means what, the specific steam consumption you can write 3600 by W net, and the unit would be kg per kilowatt hour. Okay, so this is our specific steam consumption. Okay, so in the next part we are going to do the analysis of the Rankine cycle. Each and every process, the analysis should be there. Now we are going to see the analysis of Rankine cycle. Okay, analysis of Rankine cycle means we are going from process to process, and we are going to analyze what is going to be there. Okay, so let us start with the first process. What is the first process of Rankine cycle? It is nothing but 1 to 2. Okay, that is adiabatic compression in pressure. Okay, the adiabatic increase in pressure in pump. Okay, pump, or you can consider it as compressor. The same pump acts as a compressor in air standard cycle. Okay, now here it is what? Here it is Rankine cycle, and the phases are changing all over the cycle. Okay, phases are changing all over the cycle. Somewhere it is steam, somewhere it is mixture of steam and liquid, and somewhere it is completely liquid. Okay, so rather telling it compression, okay, we are telling that it is increasing pressure in pump. Okay, why? Because compression starts from here, and this is nothing but rejection process, and it is going to take place in the condenser. Okay, and condenser, what is the work of a condenser? It converts the steam part into completely liquid. Okay, and as we have known that the exit point of the condenser is at the saturated liquid line. Saturated liquid line means it has just completed the conversion from steam to liquid. Okay, now whatever the exit point, whatever the phase of that substance in exit point, it is completely liquid. It has just converted from whole steam to complete liquid. It has just completed. Okay, with no further cooling. It is there in that certain pressure. Okay, this is a pressure, this is the lower pressure. Okay, so at lower pressure, this is at that particular pressure, this is the particular temperature and particular entropy at which the liquid can be just the liquid which has has been converted from the complete steam. Okay, now if you increase the pressure at the same temperature, you cannot go to the same condition. Okay, so the final thing is at the exit of the condenser, whatever the liquid, whatever the substance we are going to get is in the liquid form. Okay, now 1 to 2, we are talking about the process 1 to 2. 1 to 2 is what? 1 to 2 is the pumping process. Okay, and increase in the pressure in that substance we are getting. Now we need to find what is the work done by the pump. Now if you remember in the open system work, okay, we have found out open system work. In that, the work of a compressor has been found out. It is nothing but the difference of the enthalpy. Okay, it is nothing but the difference of the enthalpy. Okay, so enthalpy at point 2 and enthalpy at point 1. Now we know how to find the enthalpy at point 1 in the steam table at that particular pressure. Okay, at that particular saturated pressure, okay, you are going to find the HF. Okay, HF means the enthalpy of the fluid at that particular pressure. You are going to get the value of H1. Okay, that means here H1 must be what? H1 at low pressure. So HF at low pressure. Okay, but how to find H2? We have already known how to find the enthalpy at any place, okay, or any other property at any place. How to find it? By finding out the dryness fraction. Okay, by finding out the dryness fraction. But the concept of dryness fraction only works when the point is inside the vapor dome. Okay, the concept of dryness fraction only works when the point is inside the vapor dome. Now but the point 2 is outside the vapor dome. Okay, outside the vapor dome, so it will be difficult for us to find the enthalpy. Okay, so we have another option. Now if you remember, the work done by pump is always the negative of V into dP. Okay, negative of V into dP. Now whatever the substance it is coming out of the condenser, is purely liquid. Okay, and as it is steam turbine, Rankine cycle is steam turbine, liquid means what? Whatever the thing this is coming out is completely water only. The product coming out of the condenser is completely water. Now water is going to be incompressible. Okay, water is incompressible. So the volume is going to be constant, only the pressure increases. Okay, so that means what? The thing coming out of the condenser is complete water. Now pumping this water, we are just increasing its pressure. We cannot compress it because water is always going to be incompressible. So we are going to take volume constant. Okay, volume constant. And if you take volume constant and do the integration of dP, it is nothing but P2 minus P1. That is, whatever the pressure it has attained after the pumping process, whatever the pressure it has attained, it is nothing but pressure at point 2. Okay, pressure at point 2 means this is a constant pressure line with the help of vapor dome. This is a constant pressure line, so pH. Okay, so this P2 is nothing but pH. This is a constant pressure line. Okay, so P2 is nothing but what? P2 is the pH. Okay, and from where? From which pressure it has started the compression? From pressure at point 1. So this is P low. Okay, so this will be low pressure. Okay, and what is V? V is what? Whatever the volume of the liquid at this point. How can we find it? We can find it at a particular pressure, that is PL. Suppose this is 1 bar. Okay, in steam table we are going to find where is the saturated pressure of 1 bar. Okay, at that pressure, what is the volume of the liquid? Okay, what is the specific volume of that liquid? We are going to find out. That specific volume at that particular pressure is nothing but what? It is our specific volume at point 1. Okay, so here V would be what? V would be nothing but specific volume of the fluid at lower pressure is going to give you this volume. Pressure 2 and pressure 1 are generally given in all the cases. Okay, so in this way we can now find out what has been the work done by the pump. Okay, so this completes the analysis of the process 1 to 2, that is the pumping process. Now in the previous board we have already found out what has been the work done by pump. Okay, we have found out this as V into P2 minus P1 was giving us the WP. H1 we know. How do you know? H1 is nothing but HF. Okay, H1 is nothing but HF at a particular pressure, that is the lower pressure. Okay, now we are going to find out what is going to be H2. Okay, so that means what? First of all, we found out work done by pump. Why? With the help of this formula. Because why? Because finding out H2 was difficult for us. Finding out H2 was difficult. That does not mean H2 is not required for us. Okay, H2 is required in the next process. That is, in the heat addition process, H2 is going to be very important. Okay, so first of all, we did not find out the work done by pressure with the help of enthalpy difference. Why? Because finding out H2 was difficult. But H1 was H1, finding out H1 was very easy, and we have already, if a steam table is given to us, we can easily find out what is the enthalpy at H1. Okay, now in the steam table this thing is also given, and from the question these two things are also given. Now we can find WP also. Okay, so WP, once we have found out WP, we can easily find what is going to be our work done by pump. Okay, so work done by pump we have found out. Now we have found out what is going to be the enthalpy at point 2. Okay, now why have we found out the enthalpy at point 2? The heat addition process. Okay, if you remember the heat addition process in the Rankine cycle, okay, so the amount of heat that has been added is going to be nothing but the difference of the enthalpy at point 3 and point 2. That is the reason why we are going to require this H2, okay, or enthalpy at point 2. So the enthalpy, the heat addition is nothing but difference between the enthalpy at point 3 and point 2 will give us the heat addition. So that is the reason we need the enthalpy at point 2. The next process we are going to analyze is nothing but 223. Okay, 223 is what? 223 is nothing but the constant pressure heat addition process. Okay, now before the heat addition, the substance which has been moving around the different machine parts was the enthalpy. Okay, the enthalpy of that substance was enthalpy at point 2. How have we found out the enthalpy at point 2? It is nothing but enthalpy at point 1 plus the work done by the pump will give us the enthalpy at point 2. Now after the heat addition, the thing or the enthalpy that it has achieved is at enthalpy at point 3. Okay, now as we have told earlier, at the right side, okay, right side everything is going to be pressure vapor, and this area is known as superheated region. Okay, superheated region. Now in the steam table there are two parts. One is saturated part and one is our superheated part. Okay, so the things which we need to find out in these lines, okay, in these lines will be found out from the saturated part. Okay, but in the superheated part there is another segment. Okay, there is another segment in the steam table which is named as superheated part. Okay, now once the state of the vapor has come out of the vapor dome, okay, once the state of the substance has come out of the vapor dome, suppose at the stage 3, okay, whatever the properties are, it has come out of the vapor dome. Okay, so once it is coming out of the vapor dome, that means it is crossing the boundary of the saturated part also. Okay, this is the saturated gaseous line and this is saturated liquid line. So once it has come out from the saturation part, it is nothing, there is nothing that would be related to saturated once it has come out. Okay, so to find out the enthalpy at point 3, what can we do? There is a superheated part where you are given. Okay, so T3 you will find out, or T3 maybe they will give. Okay, T3 they will give. Okay, or by some process you need to find out what is going to be T3. Okay, because all of the name of the processes, you know, this is constant pressure process, this is isentropic process, this is constant pressure process and constant temperature process. So giving the different formulas. Okay, so we have already given the formulas for constant pressure, constant volume, adiabatic process. For all these process we have given the relation of temperature, pressure, time. So something would be given so that you can find out the temperature at point 3, or at least you can find out the at least the temperature might be given in the question. So once you find out the temperature, suppose this temperature is given as suppose 1600 Kelvin. Okay, suppose this temperature is given as 1600 Kelvin. So you need to go to the temperature. Okay, we need to go to the steam table and find out the segment of superheated region, and in that superheated region you are going to find what is going to be the temperature. Okay, so in the superheated part there will be a segment like this, T set or T superheated. Okay, so after that, in that you will find somewhere there is 1600 Kelvin. Okay, in 1600 Kelvin they will always give you the H, S, U, V, all the things will be given. So at superheated region, okay, at superheated region, the what would be the enthalpy. Okay, what would be the enthalpy? There would be one value. Okay, that value is nothing but going to be the enthalpy at point 3. Okay, enthalpy at point 3. Now why I am saying this, because if you remember what is going to be the fast flow for open system. Okay, so this is a boiler where water is going in, okay, and water is coming out from somewhere. So if you apply the fast flow for an open system, what it is going to be? It is going to be nothing but H1 plus Q equals to H2 plus W shaft. Okay, now this was the first law, neglecting the kinetic energy and potential energy changes. Okay, V square by 2 and Z1 G has been cut down because we are neglecting the potential energy and kinetic energy changes. So from here there is no shaft work. Okay, there is no shaft work. Okay, so what is the amount of heat that has been added? It is nothing but H2 minus H1. Okay, now in process 2 to 3 there is not going to be any 2.2 or 0.1, so it is going to be simply H3 minus H2. Okay, H2 minus H1 is not present in the process 2 to 3, so that is the reason H3 minus H2 has been taken. Okay, for our process this is the general case. Okay, this is the general case and this is according to our requirement. This is general case. If two states are given, 0.1 and 0.2, then this is. But here our 0.1 is 0.2 and 0.2 is 0.3. Okay, so the amount of heat which we need to find out, okay, which we need to find out is H3 minus H2. So from the steam table you can already find the H3. Okay, from the steam table part you can already find H3 and minus of H2, which has been already found out in the process 1 to 2. Okay, so if you do this, or if you find the difference between the enthalpy at point 3 and point 2, you are going to find the heat addition, okay, or the amount of heat addition in the process 2 to 3. Regarding that steam table part where you can find these values, there would be, suppose this pressure is at 8 bar. Okay, 8 bar, this pressure is at 8 bar. So for 8 bar they will already mention, okay, this is for 8 bar. For 8 bar you will find different temperatures. Okay, 1700 Kelvin, 1600 Kelvin or 1800 Kelvin, like this. You will, for this particular pressure, okay, for this particular pressure at different temperatures, what is going to be the value of enthalpy, entropy, internal energy, specific volume, all the things would be given. Now you need to find out your particular, okay, you need to find out H3. That means what you are going to find, okay, you are going to turn up the pages and you will find where the 8 bar is given, the heading 8 bar is given, like that 8 bar, 8.1 bar, 8.5 bar, like that. Different things, different pressures would be there, and under that pressure there would be a complete table. In that particular pressure there would be different temperatures. Okay, now as it is 8 bar is given, you need to find 8 bar in the superheated region. Okay, in that different temperatures would be given. At that different temperature you need to find what is the conditions, or what are the conditions at 1600 Kelvin. So 1600 Kelvin, what is going to be the value of H? It is going to be the enthalpy at point H. Okay, so from here H3 is what? H3 is nothing but value of enthalpy at high pressure, value of enthalpy at high pressure and superheated temperature. Okay, what is the superheated temperature? It is nothing but T3. Okay, at T3 and at pH, what is going to the value of H, and H2 we have already found out. Okay, so this will give us the analysis of the pressure, process 2 to 3. The next process which we are going to analyze is nothing but 3 to 4. 3 to 4 is what? 3 to 4 is expansion. Okay, isentropic expansion in turbine. Okay, isentropic expansion in turbine. Okay, so now work done by turbine is what? Work done by turbine is the difference between enthalpy at the two end points. Okay, so H3 minus H4 would give you your work done by the turbine. Okay, so this thing we have found out in the work done in open system. Okay, this thing we have found out in the work done in open system. Now H3 minus H4 would give you what? H3 minus H4 would give you the work done by turbine. Okay, now H3 you have just found out from the last board. Okay, from the steam table. Okay, from the steam table at pressure 8 bar and at temperature 1600 Kelvin, the value of enthalpy has given you H3. Okay, so H3 is what? H3 is nothing but H at higher pressure and superheated temperature would give you the H3. Okay, now you need to find H4. Okay, the process had been already discussed. Okay, how to find H4. Okay, so in this total line, the entropy is going, since it is isentropic process, S3 is going to be equal to S4. Okay, S3 is going to be equal to S4. Now, how can you find S3? Again from the steam table. Okay, at 8 bar, you will find the heading of 8 bar in the superheated region. In that, you are going to find the temperature of 1600 Kelvin. Okay, in that with H, there would be S also. Okay, S means what? Entropy. Entropy is what? At superheated pressure of 8 bar and at superheated temperature of 1600 Kelvin. Okay, what is the value of S here? This value of S would be nothing but whatever the value of S you have found out here. Okay, so from the steam table you can find what is the value of S3. Okay, from the steam table you can find what is the value of S3. So once you have found out the value of S3 from here, okay, S3 from here, from the steam table, that means you are going to equate this with S4. That means entropy at 4 is now known to us. Okay, entropy at point 4 is now known to us. Now there is another relation as we have told you earlier. Okay, S4 is nothing but S4 is nothing but S at fluid line plus dryness fraction into the difference of the entropy at fluid line and gaseous line. That means S4 is equal to what? SF plus X4 into SFG. Okay, now SF is what? SF is nothing but at that particular pressure. Okay, at that that is 1 bar. We have written here 1 bar. Okay, now this is in the superheated region. Okay, this is in the superheated region. From superheated region we are going to find what is the entropy at the superheated point S3. Now S4 is not at superheated region. Okay, it was in superheated region in point 3. After coming to point 4, it is not in superheated region now. So in this line, all the points that has been related to are in saturated region. Okay, so we are going to the saturated region. In the steam table we are going to the saturated segment again. After going to the saturated segment, what is going to be there? At that particular pressure 1 bar. Okay, as we have told earlier, in the steam table you are now going to find at 1 bar. Okay, at pressure 1 bar, okay, what is going to be your SF? Okay, what is going to be your SF? SF, that means this one. Okay, that means entropy in fluid line and pressure 1 bar is this one. Okay, and SFG is what? SFG is nothing but SG minus SF. So SF you have already found out from the steam table, and again in that pressure only, in that particular pressure 1 bar, you are going to find entropy of SG. Okay, or entropy of the substance in gaseous line in that particular pressure would also be given in the steam table. Okay, so now you know S4. From S3, equating S3 and S4, you are going to find out S4 from the steam table, from the saturated segment of the steam table, and at that particular pressure you are going to find SF, you are going to find SG, SF is already known. So all these things are known. What do you need to find now? You need to find what is going to be your dryness fraction. So X4 is your dryness fraction now. Okay, so once you find out the dryness fraction, so everything now you can find out. If you find out the dryness fraction at this point, X4 is already known to you, you can find out everything. So you can find out enthalpy also. H4 is what? H4 is nothing but HF plus X4 into HFG. Okay, HFG. Now H4 you need to find out. X4 you already know. From the steam table, at that particular pressure 1 bar, what is going to be the enthalpy at fluid line is going to give you your HF. At that particular pressure, what is going to be your enthalpy at enthalpy or HFG is also given. Okay, directly you can find the value of HFG also from the steam table. Okay, so now HF is known, this is known, HFG is known, dryness fraction is known. Now you can easily find H4. Okay, now once you are finding out the H4, you are going to find out the value of WT also, because H3 you have just found out in the last board. H4 you are just finding out now. So what is the value you are going to find out from the turbine is going to give you your total work done by the turbine. Okay, so this is our analysis for the process 3 to 4. After you find out the work done by turbine, you can easily find out now WT minus WP, because in the analysis of 1 to 2 you can find out what is the work done by the pump. Okay, it was V into pressure, difference between the pressures. Okay, so this will give you your what? This is give you W net. Q in also find out Q in, that means what is the heat input we have also found out in the process 2 to 3. So with the analysis of these processes only 1 to 2, 2 to 3 and 3 to 4, without even doing 4 to 1, we can easily find the efficiency, because all the things that are required we can easily find out. Q in has been found out in process 2 to 3, W net has been found out in the process 1 to 2 and 3 to 4. Now you can easily find the efficiency. Okay, so this completes our analysis of the process 3 to 4. Now process 4 to 1 is going to give us the condenser, okay, the heat rejection process. So 4 to 1 is constant pressure heat rejection process. Okay, now if you apply the first law again, this is not going to be nothing but H1 plus heat addition plus H2 plus W, with neglecting the kinetic energy and potential energy difference. Okay, now this is going to be 0 because in condenser there is no shaft work. Okay, so only heat rejection is there. Now heat rejection is what? Heat rejection is going to be negative. Heat is going to get rejected from the system, so this is going to be this. So Q will be what? Q will be nothing but H1 minus H4. So H1 minus H2. Okay, so this is the general case, and H1 is the initial condition, H2 is the final condition. So from here, from the condenser, it is coming in this way. So initial condition is H4 and final condition is H1. Okay, so this is going to be nothing but H4 minus H1. This is for our, okay, this is for our case. Okay, for general case H1 minus H2, it is going from 1 to 2. Now it is coming from 4 to 1. 4 to 1 it is coming from. So enthalpy difference of H4 and H1 is going to give us our Q in. Okay, or what is the amount of heat input. Okay, now if you see, we are constantly doing something that the process 1 to 2, after finding the process 1 to 2, we have found out the enthalpy. So it is like chain. Okay, without finding the one enthalpy at one point, you cannot go to the next process. Okay, so if you remember, from the process 1 to 2 we have found out H2. Okay, in the process of 2 to 3, once we have found out H2, and from the steam table we have got these 3. Okay, so whatever the enthalpy which has been found out in the first analysis from the process 1 to 2 is helping us in the next process H2 to 3. Okay, again what is going to be the work done by the turbine? Okay, for this we need to know H3, and this was found out in the analysis previous to this turbine analysis. Okay, so whatever the enthalpy that is found out in the process 2 to 3 is going to help us in the analysis of process 3 to 4. Again, in the process 3 to 4 we have found out the enthalpy in 0.4. Okay, so now again this is going to help us in finding the properties in the process 4 to 1. Okay, so without finding one, you cannot go to